Hello everyone, welcome to this presentation. This time we are going to see how to implement ideal comparators in LTspice. This is something that I have missed when using LTspice. We can find real comparators from linear technology company, for example, but we cannot find in LTspice ideal comparators that can be useful to perform simulations in complex circuits with many components, and when we don't want to simulate the exactly real behavior of the real component or the real comparator. Okay. So using an ideal comparator, then we can improve the speed of our simulation, and this is also useful. Okay, so how to implement a comparator? This is something really easy to do using LTspice. Okay, we can see in this picture that we have this comparator with the non-inverting input, the inverting input, the positive power supply, the negative power supply, and the output. Okay, so the operation of ideal comparator is just that is just the one shown here in this picture. We show the output voltage as a function of the differential voltage. Okay, the differential voltage is the difference between the voltage at the non-inverting input minus the voltage at the inverting input. Okay, so when the differential voltage is positive, then the output is going to saturate to the positive power supply voltage. And then when the differential voltage is negative, then the output is going to be equal to the negative power supply voltage. So we can express this function, this behavior, using this function here. VO is equal to plus VCC if VD is positive, and then is equal to minus VCC if VD is lower or equal than 0. So we have selected here to give negative value of the output in case that the differential voltage is exactly equal to 0. Okay, which is one of the possibilities, is the usual one. So in order to implement at the end this function here, we can use the if statement in LTspice. Okay, so we can implement our ideal comparator like this. We have used here two inputs, the positive for the positive power supply, the negative for the negative power supply. Okay, we include these resistances just to stabilize the voltage. They are not really very important. We have used here values of 1 mega ohm in order to assure that there is going to be little current circulating through these inputs. Okay, then for the non-inverting input and the inverting input, we use again a high input resistance, 1 mega ohm, and then we implement the behavior using this voltage source, behavioral voltage source, in which the value is equal to this expression here. Okay, so it is really very simple. If the voltage, okay, the differential voltage V in plus minus V in minus, okay, is positive, then we are going to get this value, okay, the voltage that we have here at this input, okay, and then in the other case, if this value here, this differential voltage is lower or equal to 0, then we get at the output the value of the negative power supply. Okay, so this is really simple to implement. Then remember, as we have seen in one of the first videos explaining how to implement components in LTspice, we need two elements or two parts. We need the description in text. Okay, so here is our description, and then we need the symbol to do the implementation. Okay, so this is the two symbols that I have developed for this component. Okay, so we can see here the description, okay, and the symbol. We can take a look to the elements that I have developed for this. For example, I have started doing this schematic here, comparator, comp, okay, with the input and the outputs. From here, we can get, going here, view and spice netlist, we can get directly the netlist, okay? So we don't need to worry about writing everything, just we can do the drawing and then copy here. We can copy this and we have the netlist and the description of our circuit, okay? So we can take this to the description here, and then we include this statement, okay, to say that this is element, a component with the name my comparator, the inputs and outputs, okay, and end with this description again as we have seen, okay. And for the symbol, I developed this symbol here, which let me see, is this one, my comparator dot asy, okay, and then I've drawn this symbol with the different pins and so on, and with this symbol here indicating that this is a comparator. Okay, so what is important is to remember the order that we have here for the inputs and the outputs. Okay, and we have to follow the same order here in the drawing of the component. Okay, so here, for example, is pin 1, which is in plus. Okay, here is in minus, which is pin 2. Okay, and so on. And this is positive power supply, pin 3. Okay, negative power supply, pin 4, and then the output, pin 5. Okay, and then here we have to go to edit attributes, and then select here the name of the spice model, the description, my comparator, a custom comparator, and then the name of the file containing the description, my comparator.suv. Okay, so this is very simple. So we can do a test of this circuit. I think I have one here, my comparator test. I think it's this one. Okay, so you can see that in this case this is the symbol of the comparator. I am applying here at the negative input a sawtooth waveform with this description. We are going to see right now the waveform, and then this voltage for comparison, okay, and the positive and negative voltages of the power supplies are 15 volts and minus 15 volts, okay. So if I run the simulation, we can see, for example, the value here, the sawtooth waveform at this point, okay, so it's a waveform going from 0 to 10 volts, okay, at 100 kilohertz. This is what I am applying to the negative input, the inverting input, and to the non-inverting input we have a value of 1 volt. We can see it here, okay, in blue. Okay, and then at the output we can see the output of the comparator. To see this better, we can increase maybe here the top to 20 volts. Okay, so we can see the outputs and maybe also the negative part to minus 20 to see well the saturation to 15 volts and minus 15 volts. Okay, so if we change here, for example, to 4, then we are going to increase the duty cycle of the output. Okay, let's run the simulation. So we can see here the output voltage. So and this is PWM, okay, modulator that we can use later in power supplies. I wanted to show how to implement this comparator because it is not available in LTspice distribution, and then we can use this in future videos, okay, that we are going to show other applications of this comparator in power converters and so on. So with this description, you can develop your own comparator. But if you want to save time, you can go to my web page. Okay, if you go to search engine and write my name, Marcos Alonso, and Uniobi. Okay, hopefully we are going to obtain this link here, which is the link to my personal web page. And then here you can find in resources, okay, in resources you can find some interesting components, and this component that we have developed in another video, in a past video, and this one, my comparator, okay, and we are going to see this other one, my comparator open collector with open collector output, okay. So this is a typical comparator with an output that behaves like a voltage source, okay, always is going to be saturating to the top level or to the bottom level, okay. Well, I've seen here, as we have seen here, okay, we can change, for example, this value, negative value, and say, for example, 0 volts, and then it's going to work properly. Okay, we have the constant voltage, the sawtooth waveform, and then the output now between 0 and plus 15 volts. Okay. But in many applications, in many cases, we don't have available this type of comparators. Usually the fast comparators are with open collector output, so it is also convenient for some applications if we want to simulate more or better the behavior of the comparator. Then it is interesting also for us to have an open collector comparator, okay, with the output in open collector. Okay, let me see here. So we go back to this presentation, and we are going to see how to implement an open collector comparator. Okay, an example is this one, the LM193. Okay, this is the schematic of this comparator, and then as we can see here, what we have in this comparator is a bipolar transistor with the collector at the output. Okay, just the collector. Okay, so when it is going to saturate to the negative value, to 0, then the circuit is going to inject current into the base of this transistor, and the transistor is going to saturate. Otherwise, the transistor is going to be open, okay, no current. The other transistor, Q7, is going to carry the current to ground, and then this transistor, output transistor, Q8, is going to be in off state, okay. So this is the operation. So when we have more voltage at the positive input than at the negative input, excuse me, then transistor Q8 is off, okay, and then when we have more voltage at the negative input than at the positive input, then transistor Q8 is going to be saturated, okay. And usually what we do is to place a pull-up resistance here to the input voltage, and then we generate a voltage at the output, okay. But we can do many other things with this type of open collector output. So this is the way to implement our open collector comparator. We are going to implement the output using a switch, okay, with the collector being the output, and we are going to have also accessible the emitter, okay, so we can connect the emitter to the ground or do other things. So our comparator is going to behave like shown on the right part of this slide. When the differential voltage is positive, then the switch at the output is going to be off, okay? And when the differential voltage is lower or equal than 0, then the switch is going to be activated, okay? So this will be the implementation of the open collector comparator. And this would be the implementation in LTspice. In this case, we need only one positive voltage. Then we have the non-inverting input and the inverting input with the input resistance in the same manner as in the other comparator. And then we are implementing the output using this voltage controlled switch. Okay. And using again this behavioral voltage source to control the switch. Okay, so the switch is defined as shown here, okay, with an on resistance of 10 milliohm, an off resistance of 10 megaohm. The threshold voltage is 0.5 volts and with a hysteretic band of minus to 0.2 volts. Okay. So then in this case, we want the switch to be open when the differential voltage is positive, okay? So in this case, when V I plus minus V I minus is greater than 0, then we generate 0 voltage here at the output, so the switch is going to be open, okay? And in the other case, when it is the differential voltage is lower or equal than 0, okay, then we are going to apply 1 voltage here at the output, so the switch is going to be in on state. Okay, and to implement this component, then we need two items, as we know already. One is the file, the .sub file with the definition of our component. Okay, so we can see here the definition, and the other one is the symbol for our component, okay, with all the inputs and outputs. So in this case, we have the non-inverting input, the inverting input, the positive voltage, the collector, and the emitter. So we can see now the implementation. First, what I did was to draw the schematic of our component. As we know, it will be like this, okay, using the ports for the inputs and the outputs and the definitions as we have seen, okay? So with this we can do a view, spice netlist, and then have here the definition, complete definition of our component. So we just have to take this, copy it, and paste this information in the other file, okay, my comparator oc.sub. Okay, so here we have the description, okay, this we have obtained this from the schematic, and then we add the subcircuit description and also the ends directive, okay, to end our definition of the component. And the other item, as we know, is the .asy component. It will be somewhere here, okay? So we can see here again both things, okay? And with all the different inputs and outputs, okay? Positive voltage, in this case the output, which is the collector here, and here we have the emitter, okay? And remember that we need to go to edit attributes, and then for this component we need to give the name of our model, the description, in this case is open collector comparator, and then the file in which we have the definition, okay, my comparator oc.sub, which is this one on the right, okay? And with this we can go and test our component I have a file here, I think is my comparator OC test. So in this case, also in the symbol, I have added these letters OC to indicate that the output is open collector. Okay, so now we can see, we can run the simulation, okay, and see the voltage at the inverting input, which is the sawtooth waveform, then the voltage at the positive input, which is our reference, 6 volts in this case, and then note that in this case we have connected the emitter to ground and then the output, the collector, using the pull-up resistance to the positive voltage. Okay, so if we look at the output, then we can see that we have a positive voltage. It is better to use here, for example, 20 volts. And then we can see that when the reference voltage is higher than the sawtooth waveform, then we have at the output 15 volts, okay, saturated the output to the positive value. And then in the other case, when the reference voltage is below the sawtooth waveform, then we have 0 voltage here at the output, okay. So this is one possibility, but we can do more things, other applications typical when we use open collector outputs to implement, for example, hysteretic comparators and so on. So this is all from this presentation today. Thank you very much for watching this video. Let me know if you have any comment and see you in another video. Thank you very much and goodbye.